Here is the mystery solar system question, dealing with how the motion of a planet affects how things appear to move in that planet's sky. We'll be looking at applying both the spin and orbit of the planet to see how these affect the view. There are 4 parts to this question. The first part asks how long the planet's day is in Earth hours. This is really easy since this is given right on your mystery solar system table. Remember, it's the spin of the planet that determines how long its day is. So you can just copy the value straight off the table. It's already in the right units. The other parts take a little more work. Part B asks you to figure out how long the planet's year is. This is easy too, but you also need to convert the value into a couple of different sets of units. Then parts C and D ask you to talk about how things appear to move in the planet's sky. In part C, you're looking at the motion in just a few hours. The trick here is that the planet spins at a different rate than the Earth does, so the timing will be different from what you experience on Earth. In part D, the motion is over several Earth months. Once again, you'll need to look at how the different length of the year affects how long it takes for the view from the planet to change. Now let's look at parts B, C, and D in a little more detail. Part B focuses on the length of the planet's year. We already know that a year is defined by the planet's orbit around its sun, so you can use the orbit period from the mystery solar system table. This period is given in years, so you can use that value directly for the first part of your answer. But you also need to give this in a couple of other units. The first one is Earth days. This is simply a unit conversion, just like we've talked about earlier in the course. Since there are 365.25 Earth days in an Earth year, to find the number of Earth years, all you have to do is multiply the length of the planet's year by 365.25 Earth days divided by 1 Earth year. You should be able to check your result fairly easily here. If the planet's orbit is less than 1 Earth year, then you should get less than 365.25 Earth days. If it's more than 1 Earth year, then it should be more than 365.25 Earth days. The last set of units to convert to is the planet's days. Since the planet isn't the Earth, its days are generally a different length than Earth days, so the number of days in the year will be different. At the moment, we know the length of the planet's days in Earth hours. That was our answer to Part A. So our first step is to convert the planet's year into Earth hours. Since there are 24 Earth hours in 1 Earth day, just multiply the length of the planet's year in Earth days by 24 hours divided by 1 Earth day. That should give a pretty big number. Most planets will have years that are thousands of hours long. Finally, we can multiply the length of the year in hours by 1 planet day divided by the number of hours in the planet's day. That gives us the total number of planet's days in the planet's year. Once you've got an answer, decide if it makes sense. If the planet's year is longer than Earth, and its days are shorter, then you should get a lot more than 365 days in the planet's year. If the planet's year is short and the days are long, then the number of planet's days should be a lot less than 365. An extreme case might be when the planet has a spin that is thousands of hours long. If the spin takes as long as the orbit, then the planet is called a one-face world. It always keeps the same side towards its star, just like Earth's moon always keeps the same side towards Earth. Later, we'll look at why this can happen for moons and planets. Let's look at an example of finding the length of a planet's year. What makes this a bit of a challenge is that we have to keep track of a bunch of unit conversions. Let's consider a planet that has an orbit of 1.2 Earth years and a spin of 16 hours. Right away, we know that the planet's day is 16 hours long. That's our answer to Part A. Also, we know that the planet's year is 1.2 Earth years long, about 20% longer than an Earth year. To convert the planet's year into Earth days, we multiply 1.2 Earth years by 365.25 Earth days per Earth year, and that gives us 438 Earth days. As we expected, this is more than 365 Earth days. Next, we need to convert to hours. Just multiply 438 Earth days by 24 hours per 1 Earth day, and that gives about 10,512 hours. Finally, to convert to planet days, we just multiply these hours by a conversion factor of 1 planet day divided by 16 hours. This gives us 657 planet days in the year. This is a lot more than Earth's, but that's not surprising, since the planet's orbit takes longer than the Earth's does, and its days are shorter. Now let's look at how the view of the sky changes over time. Here on Earth, we know that our planet spins once every 24 hours. If a constellation is overhead at midnight, in 6 hours it will be low in the west, and in 12 hours it will be straight under our feet. But that will be different if you're on a different planet. If a planet spins slower, then 6 hours after midnight the constellation will still be above the horizon in the western sky because the planet hasn't spun very far. If the planet spins faster, then the constellation will have set and the sun come up. A good way to get a sense of what is going on here is to draw a picture, which is why the question asks you to do this. Remember that your picture has to show why the view is changing. Since it's the planet's spin that causes things to rise and set, you're going to have to show the view from space looking down on the planet's north pole. That way, you can show how the planet is spinning over time. Note that your picture doesn't have to be fancy. Just a couple of circles with arrows and labels work fine here. This picture shows you a planet and its sun. Since midnight happens on the side of the planet facing away from the sun, that's labeled as well. We've also labeled a constellation that is straight overhead from that midnight location. To figure out if the constellation is still in the sky 6 hours later, you should divide the number of hours in the planet's day by 4. That tells you how long it takes for the planet to make 1/4 turn, and then you can tell whether 6 hours is long enough for a constellation to set below the horizon. In the example we just covered, the planet spun once every 16 hours. So let's see how we answer this question for that planet. With a 16-hour spin, that means that in 8 hours the planet spins halfway around, and it makes a 1/4 turn in just 4 hours. So in 6 hours, the planet has spun more than 1/4 turn, and hence the constellation has set for our observer on the planet. So we would say that the constellation is below their western horizon. In other words, they would have to be able to look through the planet to see the constellation. Now that you've seen how the planet's spin affects the view, try using a similar approach to the planet's orbit. Make a diagram similar to the one you did for Part C, only this time you're going to have to allow for the planet's orbit around its sun. You're going to have to look at your results from Part B to see how far the planet will move in its orbit in half of an Earth year. It might be less than halfway around its sun. It might be more than half. It could even be more than 1 full orbit if the planet's orbit is especially quick. Once you've figured out where the planet is in half an Earth year, label the midnight location on the planet, and then use that to figure out whether you will see the constellation from there or not.